Hello everyone, my name is Seungwon Kim, and today I'll talk about my paper, Mind the Gap, Injecting Commonsense Knowledge for Abstractive Dialogue Summarization. In this paper, we use commonsense knowledge inferences as additional input and supervision signal to guide the model to generate a richer summarization result. Before getting started, I would like to thank my co-authors for helping me finish this wonderful project. Compared to the conventional document-to-document summarization such as news article summarization or scientific publication summarization, dialogue summarization has its own unique difficulty due to the input-output format discrepancy. Since the input is a dialogue, it has different characteristics compared to documents. First, the unspoken intention is crucial for understanding the utterance. For example, without understanding that the intent to make fun of someone from Derek's utterance, you couldn't understand the dialogue's overall context, and it'll be difficult to generate a good summary. Second, there exists information that could be understood when its hidden meaning is revealed. For example, it is important to capture that, yes, that's ancient by laptop standards, means the laptop is too old from Melody's utterance, and therefore, you have to understand this hidden meaning in order to generate a good summary. To overcome these issues, we use commonsense inferences generated by Comet, a transformer-based model that generates commonsense inferences when a text input is given. With commonsense inferences, we thought we could both find the unspoken intention and the hidden meaning of utterances. So during the early experiments, what really surprised me was that Comet works quite well for dialogues as well, although it wasn't a model explicitly trained for dialogues. Besides Comet, we also experimented with Paracomet, an advanced version of Comet that considers previous context of the text input using an internal memory module. On Table 1 and Table 2, you can see some of the examples that Comet generated. Each inferences reveal different aspects of the utterance based on which commonsense relation was used to generate a commonsense inference. So here's our proposing framework SICK that stands for Summarizing with Injected Commonsense Knowledge. SICK consists of three main steps. The first step is commonsense generation and selection. We take each utterance from the dialogue and pass it to Comet. For each utterance, we use 5 different commonsense relations and generate 5 different inferences for each relation. Therefore, for each utterance, 25 commonsense inferences will be generated. Then, using SentenceBird, we compare the similarity score between the utterance and the 25 commonsense inference candidates, and choose the most probable commonsense inference as the final commonsense inference for that utterance. We've tested 3 different variants for commonsense selection methods, and the similarity score-based method achieved the best performance. I'll talk about more of this on the later slides. The second step is training the model with commonsense inferences as additional input. We cross-concatenate the utterance and the commonsense inferences as in equation 2 and pass it to our model. We train with a cross-entropy loss as a usual sequence-to-sequence learning problem would do. The last step is commonsense supervision, what differentiates SICK and SICK++. For SICK++, we do the same process of commonsense generation and selection, but this time for the summary itself, not the input dialogue. So if the golden summary consists of 2 sentences, we get 2 additional commonsense inferences. However, it doesn't make sense to generate the summary and its corresponding commonsense inference at the same time, since what we really want is the summary, not the commonsense inference of the summary. Therefore, we add an additional decoder to the model and a following loss term of generating the commonsense inference of the summary. Then, we train the model with 2 loss functions. The datasets we use to experiment with SAMSUM and DialogueSum, 2 mostly used datasets in this field. The upper group are pre-trained language models, and the second group are techniques or frameworks that are specifically designed for dialogue summarization. Besides the competitive results, what really excited me the most is that SAMSUM and DialogueSum aren't actually datasets explicitly made for common sense reasoning. techniques made for common sense reasoning mostly use common sense reasoning benchmarks such as HellerSwab, Social IQA, COPA, but I think it's really impressive to see that common sense helps in other general data sets as well. This is one of the experiments from the appendix section, where we tested different generation models and selection methods. Conventionally, a lot of common sense reasoning papers use the NLI-based method as their selection method to choose the most probable common sense inference, where an inference with a high entailment score and a low contradiction score would be chosen as the most probable common sense inference. Among different variants, we found that the similarity-based method works best for both generation models. Furthermore, we conduct 3 additional experiments to show the effectiveness of SIG and SIG++. First, we wanted to see if adding common sense inference actually helps the model. However, in the main results section, there are a number of factors that could influence the score, such as hyperparameter settings. Therefore, we adopted a zero-shot setting where the only difference between SIG and BART X sum is whether we added common sense inferences as additional input or not. You could see that simply adding common sense inferences helps the model to generate better summaries. Second, generating and selecting a good set of common sense inferences is quite costly, but shows improvement in performance. We conjecture that in a low resource setting, where only a subset of dataset is given, our method could work well compared to the naive setting. You can see that in the Rouge 1 metric, using only 30% of data with SIG++ achieves better performance than the naive setting with 70% of data. This is strong evidence that the additional knowledge provided helped the model to generate better summaries. Lastly, we wanted to check if the auxiliary task of generating common sense inferences of the summary helped. In other words, we wanted to check why SIG++ achieved better performance compared to SIG. When we look at the attention visualization, we can see that SIG++ has higher attention values at the upper layers. A lot of Bertolacci papers have mentioned that the upper layers of transformer-based models are responsible for understanding the overall context of the input, while the lower layers try to understand the lexical meaning of the input. We see this as strong evidence of common sense supervision task. The task of generating the common sense inferences actually helped to ground the model to actually use the common sense inference inputs. So thank you for listening to this presentation, and please feel free to ask any additional questions of the paper via email. Thank you.